You ever wonder what's really going on inside your phone, or your laptop, or even just the light switch on your wall? It can all feel like magic, but it's not. It's actually a pretty simple and really elegant set of rules. Today, we're going to pull back that curtain on the unseen world of electric circuits. We're going to get to the bottom of the fundamental principles that power, well, literally everything around us. Okay, let's jump right in. So, here's the game plan. First, we're going to meet the basic building blocks, the real movers and shakers of the circuit world. Then we'll get into the rule of resistance, which, by the way, is the reason your phone charger gets warm. After that, we'll see how engineers take real-world stuff and turn it into simple diagrams. And then we'll cover the two unbreakable laws that hold the entire universe of circuits together. And finally, we'll uncover the shocking truth about electrical safety.
All right, first up, let's meet the cast of characters. At its heart, any circuit is just a story about energy. It's about energy being created and energy being used. And that means we can basically split every single component into one of two fundamental groups.
So on one side, you have your active elements. These are the givers. Think of a battery or the power supply for your computer. They are the things capable of actually generating electric energy. And on the other side, you've got your passive elements. These are the takers. They can't create energy on their own. Instead, they absorb it or store it or just get in its way. It's kind of like the difference between a powerful water pump that's pushing water through a system and a really narrow pipe that just restricts the flow.
So let's talk about these energy givers. The first one is an ideal voltage source. You can think of this as a perfect, tireless pump. Its only job is to maintain a constant electrical pressure, that's the voltage, no matter how much water or current you try to pull from it. It's the steady, reliable heartbeat of the circuit.
Now, the flip side of that coin is the ideal current source. This one is all about the flow. Its whole purpose is to make sure a perfectly constant amount of current is moving through it, no matter what the voltage has to do to make that happen. It's a little less common to find in the real world than a voltage source, but it's an absolutely crucial concept for understanding how circuits work.
Okay, so now we have our sources, and they're pushing all this energy into the circuit. But what are they pushing against? Well, that brings us to maybe the most common property of all, resistance.
Resistance is, well, it's exactly what it sounds like. It's a material's natural tendency to resist or get in the way of electric current. Everything has some amount of resistance. We measure this electrical friction in a unit called the ohm. And what's really important to get is that this isn't some flaw. It's a fundamental property of the universe that we actually use to our advantage all the time. And this brings us to the beautiful, simple relationship between that push, that flow, and that friction. This is Ohm's law, and it is the absolute cornerstone of circuit analysis. It's just a simple little formula that says the voltage, that's V, across something is equal to the current, I, flowing through it, multiplied by its resistance, R. It's so simple, so elegant, and unbelievably powerful.
Let's make this super real for a second. We've all felt this, right? You unplug your phone after it's been charging for a while, and that little power break is warm, maybe even hot. Why? What's going on there? Well, it's not magic, it's physics, and it is a direct result of resistance.
See, that warmth you feel? That's energy that's being converted into heat. And as this formula shows, that power dissipation comes from the current flowing through resistance. This is exactly why engineers have to design things like metal fins, heat sinks, or even little fans into powerful electronics. They have to manage all this unavoidable heat to keep the components from literally melting.
Now, one of the most critical skills in all of electronics is abstraction. It's the ability to look at a really complex physical thing and boil it down to just a few simple symbols on a piece of paper. This is what we call making a circuit model. And what's so cool about this is that the symbol for resistor doesn't just represent, a resistor. That little zigzag line can be used to model the glowing filament in an old light bulb, or the heating coils in your toaster, or even the conductive metal case of an appliance. The symbol isn't the object itself, it represents the property of resistance. A perfect example of this is an ideal switch. When it's in the on state, we model it as a short circuit, basically a perfect wire with zero resistance. All the current flows right through. But in the off state, it becomes an open circuit, a gap with infinite resistance that completely blocks any current from flowing. It's the ultimate all-or-nothing component. So we have our elements and we know how to model them. But what happens when we start connecting them all together? Well, for that, we need two foundational laws, named after a guy named Gustav Kirchhoff. And these laws are true for absolutely any circuit you could ever build, no matter how ridiculously complex it is. First up is Kirchhoff's current law, or KCL. Now, the formal definition says the algebraic sum of all the currents at any node equals 0. Okay, that sounds pretty academic, right? All algebraic sum means is that we pay attention to direction. Current going in is positive, current going out is negative. But what does it really mean?
It's simply the intersection rule. Just think of a node in a circuit like a junction, where a bunch of water pipes meet up. You can't just create or destroy water right there at the intersection. It's impossible. So, the total amount of water flowing in has to be exactly equal to the total amount of water flowing out. Current works the exact same way. It can't just disappear into thin air.
And the second unbreakable rule is Kirchhoff's voltage law, or KVL. This one says that the sum of all the voltage changes, the gains and the drops, as you go around any closed loop has to add up to 0.
This one is the round-trip rule. Imagine you start at a water pump. You get a big boost in pressure. Then, as you go all the way around the system of pipes, you lose bits of pressure because of friction. By the time you get back to the exact spot where you started, the total pressure you gained from the pump has to equal the total pressure you lost along the way. You're back where you started, back at 0. It's a perfect balancing act of energy.
Okay, we've talked about elements, resistance, and these fundamental laws. But why does any of this really matter to you in your everyday life? Well, because understanding these basic rules is the absolute key to electrical safety.
We're always taught to be scared of high voltage, but that's really only half the story. The real question, the one we should all be asking, is this: how much current flowing through a person's body does it take to be dangerous?
Just take a look at these numbers. It's pretty sobering. Only 5 milliamps, that's 5,000ths of an amp, is considered the maximum harmless current. By the time you get to 50 or 100 milliamps, you're talking about ventricular fibrillation. That's when your heart's electrical signals go completely haywire and it just can't pump blood anymore. And that is very often fatal. The key thing here is that it's not the voltage that gets you, it's the current that the voltage is able to push through your body's own natural resistance.
And that right there is the big takeaway. When you get an electric shock, your body becomes just another component, a passive element, a resistor in the circuit. So all of electrical safety, really, isn't about avoiding voltage. It's about preventing your body from becoming a pathway for current to flow. You literally become part of the circuit diagram. So we've seen that underneath all the incredible complexity of our modern gadgets, there are these beautifully simple rules of pressure, flow, and resistance. They define everything about how energy moves and how we can control it safely and effectively. So I guess there's only one question left. Now that you know the rules, what are you going to build?